Okay, here we go. 4.2, part 1, sigma notation. So let's look at sigma notation. We did this in honors pre-calc. Let's take a second look and remind ourselves that we're going to see the Greek letter sigma, and that indicates we're taking a sum. And we are going to know where we start. That 1 is our lower bound of our summation, and where we end, that n, represents our upper bound. And we're going to use I as the index of summation, though sometimes you can also use J or K. So here we go. Let's look at example 1 to remind ourselves what we did last year. So this tells us that our rule for our summation is J squared. So in this case, J is our index of summation. So what this says is start with J being 3, so we plug 3 into the rule, and then we could just keep going until we reach our upper bound of 7. So I'm writing out what this summation says, and then you just go ahead and pick up your calculator, and let's see if I pick up my calculator or pick up my notes, and I've got that equals 135. And so the example 2 has something different going on because we do have a rule that involves k, right, the k squared plus 1, but then we see this n. And so we notice, though, n is actually really a constant because n stands for whatever our upper bound is. That's going to be a constant. It's going to be a number. So we're going to go ahead and realize that for each one of our terms that we're adding up, that 1 over n stays. And we're just plugging in the 1 for k, and then the 1 over n stays, right? And we're plugging in the 2 for k. And we could keep going and going, but we're going to, right? How do we keep going and end at n? We're going to show that we keep going and going by our dot, 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 pick up another plus, and then we're going to say, look, we're always going to have that 1 over n in place, and eventually our k is going to get to n squared plus 1. All right. And we'll come back to example 2 and talk about what we can do when we do have a constant as part of our summation. And so here, example 3 is just a little peek into how we're going to use summation in the future. And basically, the only thing that we're plugging into is that little I. So this says we're going to have our first term would be f of x sub 1, right? Because our lower bound is 1, delta x plus, right, we could put a 2 in there, and we keep going, but we don't, how do we keep going and how do we know where to stop? So we're going to go ahead and put the plus dot, dot, dot. That tells us we keep going until we hit the nth term, right? F of x sub n times delta x. And so in addition to understanding summations by expanding them, we also want to be able to look at an expansion of a series and be able to write that sum, right? So we're going to go ahead and we know that sigma notation, we need that Greek letter, and we know we're going to have a start and we're going to have a finish. I'm going to use J this time, and I know J is going to equal something, and then I'm going to have an upper bound on the top. So I look at the rule, and the rule, when I write here, you know, after the sigma, though I'm going to take away that square so you don't think you need that, every single term has that 5 in the numerator. Every single term has that 1 in the denominator and a plus, right? So we have that 1 plus. And then the thing that changes each time is the first time it's a 1, the second time it's a 2, the third time it's a 3. So right, this is the first term of my sequence, this is the second term of my sequence, third term of my sequence. And so basically, our third term, I keep saying sequence, but I mean sum. The first term, second term, third term. And so what I'm really doing is J is going to be what I'm plugging in each time. And I'm going to start with J equaling 1, and I'm going to end with J equaling 15. So if you saw this summation notation, you would know that we would expand it in the way that it was given to us. All right, so now we've got some properties and some summation formulas that are important and we need to commit to memory. The first one makes sense, right? If k is a constant, then I can always pull that constant out of the summation and end up whatever the summation is equal to, I just multiply it by the constant. And let's go back to number 2, and I'm using purple this whole time, so let's use some green. See how 1 over n is actually a constant because n is our upper bound? Look at this expansion of the summation. Isn't it true I could have just factored out the 1 over n and multiplied it by the 1 squared plus 1, right, plus the 2 squared plus 1. So that's all this first property is telling us. If we have a constant, we can pull it in front of the sigma and just multiply it by whatever our summation is. The second one saying if we're taking the summation of something plus something or something minus something, we can break it up into 2 different summation formulas. And that's going to be helpful when we're looking at something that's complicated together but much more easier to attack separate. And then we're going to look at these summation formulas. I know that I included this because I thought it was a really cute story. You can pause the video, it's on your paper, you can read it. But this is how we end up with these summation formulas and theorems when people actually try to sit down and do a time-consuming problem and they notice, because of patterns, shortcuts that turn into theorems, right? So that's a really cool example of that. You can stop and read that. And so basically, this makes sense, right? The summation of C, if C is a constant, right? C stands for that constant. Let me turn that over, would be C times N. What I want to focus on right here, this one we're going to build off of to remember this and this. So when I'm doing the sigma of, the summation of I, starting with 1 and my upper bound being n, then I know that I can shortcut that if I just keep going. Like, let's say I have sigma of, we're starting with 1 and we're ending with 4, and it is I. All right, I could take the time and say, well, that's 1 plus 2 plus 3 plus 4, right? That's a pretty fast thing I could do. But, wonder if they said, 40, or 400. That's going to take a lot of adding. And so what the shortcut is that you're just going to take the n times n plus 1 over 2. So in this case, if it's 400, right, we'd have the 400 times the 401 divided by 2. I know I said times 2, but I meant divided by 2. So this is a shortcut. We have to memorize this. And then what I want you to notice is that if we look at this one, look what it's done. It takes this and it squares the n, it squares the quantity n plus 1, and it squares the 2 and the 4. So if we memorize number 2 and we think, now this is, once again, this is just how I think, how do I get to I cubed? Well, I take from I take the I times I squared. And this is going to remind me to square the n plus 1, and the 2 to get to this formula. Pretty easy way to memorize it. You can choose, but I'm just telling you, we need to have these memorized because we're going to use them. And then same thing, I'm going to go ahead and get rid of all this that I wrote. If we're looking at the third summation formula, we realize that this first part, it's shared, the n over n plus 1 is shared with this. And then, so what's the difference? Actually, it's this whole thing is shared, and then we're really multiplying it by the 2n plus 1 over 3. So once again, that's one way to remember that this formula, how to memorize it. It's up to you. I'm just trying to show you some different ways that you can memorize it, but there's no getting around it. We're going to use them, and we need to memorize them. So here we go. We're going to use everything we just talked about. The fact that we know that we have a lower bound of 1 and an upper bound of n, and the fact that we have properties and a theorem, the theorem 4.2 to use. Here we go. Are we ready? So the first thing we're going to do is we're going to rewrite this. And the reason why we're going to rewrite is that I see that n squared. And if I factor out the 1 over n squared, and I'm left with I plus 1, then I'm like, 1 over n squared is a constant, and I can pull that out, right? Because n just stands for a number. My upper bound is a number. So I'm going to pull that 1 over n squared out because that is a constant, and I'm allowed to pull that out. And then I've got, let me write my lower bound and my upper bound. I've got, the upper bound's kind of way up there. And then I've got my I plus 1 left, and then I'm like, I can break this up, right? That plus tells me that I can break this up into I plus 1. You guys agree? So I used my first two properties right off the bat. I used the pulling out the constant in the front and then separating the two terms with the sigma. So now I'm going to go ahead and I think the thinner size works better. Here we go. So now I'm going to go ahead and say, wait a minute, I know this. This is my 4.2, my number 2, right? So I know that I can simplify that as, I can simplify that as n squared. I'm sorry, I'm skipping a line there. I can simplify that as n times n plus 1 over 2. Right? And then this one right here, 1 is a constant, right? So that's going to be using theorem 4.2 number 1 that says it's the constant times your upper bound. And so that's going to be plus 1n. And then I'm going to go ahead and do some magic, aka algebra. So I end up with, I'm going to do as many steps as possible so that I don't lose anybody. And then I'm going to go ahead and get the common denominator. Though I think I did that here, so let me come back because that's ridiculous. I'm going to be having 100 steps. So I wrote 1n as 2n over 2, so I could bring them all together. So I've got my n squared plus n plus 2n, so it gives me n squared plus 3n. And now I see that I can factor the n out. I've still got my constant pulled out, but I can factor the n out of the numerator. And when I do that, I can see that that will cancel out with one of these n's. And so what do I have left? I have n plus 3 over 2n. All right. Now, do I know what n is? Well, that's the second part of the problem. So let's just stop for a second. And I want you to realize how much went into it. Let me change colors so we can see what we used. First we used where we recognize that this is a constant, so that's allowed to get pulled out. That was your property number 1. And then we are allowed, when we notice that we have two terms separated by a plus sign, we can split it into two separate summations, and that was also your property. That's a second property that we used. And then we noticed that, ooh, this is my 4.2 theorem, and that's my number 2, and so I memorized that that's the same thing as this. Same thing if I'm taking the summation of a constant, that is my theorem 4.2 number 1, so I know it's a constant times the upper bound, which is n, and then I just did algebra. So now we're going to go ahead and find when n is 10, so when our upper bound is 10, what's our sum? Upper bound's 100, 1,000, and 10,000. So let's go ahead and set up a little table. But now look what we did in knowing that, let's just do our sum. So when let's do our, this is really our n, so not x and y, and then our sum. So when our n is 10, we're just plugging it into this formula, and we're going to get 13 over 20, which we're going to use as a decimal because we're going to watch how it changes. Decimal form is the best way to see that. And so then when our n is 100, we're going to plug 100 in both spaces and do that in our calculator, and we'll get a 0.515. When we throw a 1,000 in there, into our n, we're going to get a 0.5015. And when we throw 10,000 in, we're going to get 0.50015. So we can see if we kept this up, what do we think it's approaching as our upper bound increases with outbound, it increases to infinity, what do you think we're going to approach? Absolutely. I think it makes sense to say that we're going to approach 0.5, and so let's find out if that's true. So our second problem says find the limit of this sum as n approaches infinity. So aren't we glad? Because if we started the lesson with this, we'd be like, what? How are we going to solve this limit problem? But we already used our new knowledge of summations to say that that is the same thing as n plus 3 over 2n. So now we're finding the limit of n plus 3 over 2n as n approaches infinity. Now we can do this. This is This was last year's stuff, right? So we're going to go ahead and look at our denominator, our highest power as well. We only have one variable, but it's n raised to the first power, so we're going to divide everybody. I'm going to remind myself that I'm in a limit problem. We're going to divide every single term in the numerator and denominator by n. We're going to do some canceling out, right? So let's say 1. I'm going to rewrite this because sometimes when people cancel out the n over n, they think it's gone, like gone for good. Nope, it's there. It's still there, right? And then we have a 2 down here. And then as n is approaching infinity, the fraction 3 over something, a 3 over denominator that is increasing without bound is approaching 0. So then our limit is going to be 1/2, which is of course the 0.5 that we were predicting. So pretty cool, right? Because if we started the lesson with trying to do example 6, our minds would have been blown. But yet we did step by step and we are good to go. And so this is part 1 of 4.2. The second part I really should say it's 3 parts, because part 2 is you're going to do the introduction to integration worksheet, which is about the train problem. You'll be doing area under a square where you're just going to be approximating. And I want you, as you're working on that train worksheet, I want you to be checking your work using the key on the blog as you go. So it's kind of an exploratory worksheet, setting up a concept. And then when you're done with that, I want you to do the book work. The book work covers both parts of the lesson. And then our second part of the lesson next class is we are going to combine the two and do a few more problems in this section. All right, thanks for joining me. See you in class.